everybody to today's colloquium. It's our pleasure to welcome Amir Yacoby from Harvard University to present today. Amir is one of the leaders in mesoscopic devices and quantum measurement of quantum systems. I think that for me, I think that's what describes Amir, and he's done numerous things. But the other interesting thing is that about Amir is that it's great for theorists to talk to him because it feels like we almost speak the same language, and that's because Amir got his master's in theoretical physics actually, and then I guess he saw the light and he got a PhD in experimental physics from Weizmann Institute of Science. Okay, I don't have the full CV, but then he was a faculty member at Weizmann for some time, and then he moved to Harvard.
2006.
2006. Right. So right, and Amir's a member of the National Academy of Sciences, American Academy of Arts and Sciences, and several other societies. So he is a leader in the field.
Thank you. All right, so good afternoon. I'd like to thank Mohammad and a few others here that have invited me to give this colloquium and tell you about some of the work that we've been doing to look at new ways of looking at quantum materials. And I'd like to start from, somewhere that we all are familiar with, and that's how we started exploring the world around us. And, this started many, many years ago, of course, and our main tools were just our senses. So we'd look at the rainbow and could explore some diffraction of light. We'd look at the motion of the planets and consider gravity, look at tides and understand the relation between the moon and Earth. But it was rather limited. And of course, today, our understanding of nature is vast. We know that the universe began more than 13 billion years ago. We know a lot about the formation and how this progressed over time. On a more earthly scale, we know that everything around us is made of atoms, and that even though we can see matter, atoms are already hard to visualize directly. Atoms themselves are made of electrons and nucleus. The nucleus is made of protons and neutrons, and then that breaks on further. So really the question is, how do we know so much? And of course, the answer is in our ability to devise instruments that allow us to communicate our senses with nature, with what's going around us. And as Jay mentioned, I started out as a theorist, but when I transitioned to experiment, I started to look at the instruments in my lab, and I realized that most of the instruments do not report the quantities that they measure. And so partly the subject of today's talk will be, what do instruments measure? What is actually going on in an instrument? And I'd like to start with an example that is familiar to all of you, and that's GPS, global positioning system. We have it in many, many different situations, in your pocket, in your watch, in your car. It reports our position, and it does it with fantastic spatial accuracy. But really, my question is, what does it measure? This is a question to the younger members of the audience. What does a DPS actually measure? It tells us our position, but it doesn't measure our position.
time.
Yeah.
Is it time delay to various satellites?
That's right. It measures time. So it measures the time it takes. So the satellites, we have a whole variety of satellites orbiting Earth. And the only thing they're doing, they're very passive. They're sending signals towards Earth. And the signals carry a timestamp of when the signal left the satellite. And what your handheld is doing is basically measuring what time that signal arrived. And from that, it tells us, basically, it knows the time. But the hard part here, and that's the thing that not many people tell you, is that the way to connect between time and position actually requires a very sophisticated chapter of physics, theory of general relativity, and it takes into account the curvature of the Earth, of the gravitational, of space, due to the gravity of Earth and the Moon, and only when you account for these, you can get the precision in which we're reporting our position. And so the point I'm trying to make is that a measurement apparatus reports a quantity that we're interested in. Usually it's going to measure a very different quantity, and the way you connect these two is by a piece of physics that you understand, or we understand, and we can rely on. We know its limits, and that allows us to basically explore quantities that we don't know how to measure. So in the spirit of today's talk, basically what we know now is, now we know how to report position. I'm going to basically say, so now we know how to measure position. And we can continue this process many times. So we can now that we know our position, we can measure it, we can use some additional pieces of physics to report additional quantities. So for example, if you're driving in your car and you know your position, and you have another measurement apparatus that tells you what your velocity is, you can use kinematics to report your estimated time of arrival, et cetera, et cetera. So in my group, we spend a lot of time devising instruments, and when I mean devising instruments is sometimes really devising new pieces of hardware, but often for the same piece of hardware, we'll be exploring different pieces of physics that will allow us to connect the quantities that we know how to measure with the quantities that we're interested in reporting. And the hard part is really identifying that piece of physics that makes this connection, and it's going to be different for different quantities that we'd like to report. More specifically, in my group, we're exploring different ways to use circuit QED, superconducting circuits, very appropriate for today's announcement of the Nobel Prize, to explore various material parameters. So the question that you immediately need to think is, what is the connection between the things that we know how to do and measure and the quantities we'd like to report? We're developing various sensors that we can put on probes to be able to measure local potentials, local magnetic fields, and I'll talk more about these today. I'm going to give two examples of sensors that we have been developing. One that measures local potentials with spatial resolution, and the other is local magnetic fields, and I'll give some examples of the physics that we use in order to connect these quantities to interesting material properties. So before diving into each one of these techniques, I'd like to just give a little bit of motivation. Why is it that we need to develop more tools? After all, you all know we have quite a sophisticated toolbox already. What do we need? More measurement techniques. What is it that remains to be explored? So, of course, electrons, as you know, are fundamental particles, but that's only in our universe. It turns out that inside materials, where there are many, many electrons that are interacting, emergent properties of these materials arise, and we end up with a whole new variety of particles. At least that's what theorists tells us. And what we'd like to do is to develop techniques that actually visualizes some of the properties of these particles. And I'd like to give just a few examples of particles that exist in various materials under certain various conditions. So under certain conditions inside materials, these could be magnets that have interesting spin-orbit interactions, for example, or quantum Hall systems. it turns out that there are emergent particles known as skyrmions. They carry a charge of E, but they carry a spin that's far greater than a half. And in fact, that spin has a texture, either in real space or momentum space, that is topological. And in some instances, these particles are being explored as storage units for memory. Another example here are what's known as composite fermions. These are particles that arise when you subject a material to the electron system to very, very strong magnetic fields. As you know, an electron in a magnetic field moves in circles. These particles, composite fermions, actually stop moving in circles when you subject them to very strong magnetic fields. Then they start actually moving in straight lines. When you deviate from a very high magnetic field, then they start moving in circles. But they behave quite differently from electrons. They still have a charge of E. Another type particles that I'll talk about today, the visualization of fractionalized charge. So under certain conditions, even though in vacuum electron is a fundamental particle, inside a material, it's no longer the fundamental excitation, and you can have particles that are fractionalized. They carry a fraction of the electron charge and even have some really interesting non-abelian statistics, statistics that deviates from fermionic or bosonic. And while these three examples all carry a charge, there are of course also excitations inside solids, particles that are neutral. For example, spin waves is an example of a neutral excitation that can exist in solid, and it has a quantized spin equal to 1/2, but no charge. So I hope this kind of motivates why having new techniques that allow us to maybe visualize some of these conceptual constructs that theorists come up with and see really, do these particles exist or not, and what can we learn about them. So what I like to do today is tell you about these two probes that we've been using over quite some years now. The first one is a sensor that probes magnetic field as a function of position and frequency. And the second example would be a sensor that probes potentials with very high spatial resolution. And I'd like to give some examples of why these sensors have been useful. How have we been using them? All right, so the first example is a magnetic field sensor. And here again, I want to describe the physics that connects the quantity that I'd like to report. I'd like to report magnetic fields. The question is, what can I measure and what system can I measure that will allow me to report the magnetic field? And here we're using a defect in diamond. These are known as nitrogen vacancy centers. Nitrogen substitutes one of the carbon atom, and then there is a missing carbon atom nearby. This axis between the nitrogen and vacancy, as you'll see, allows us to measure magnetic fields along this axis. So in fact, it's a vector magnetometer. And the nice thing about this defect is that it lies really deep within the diamond band gap. So it's very, very isolated from anything that happens in either of the bands. The valence band is just full and inert, and the conduction band is empty and inert. So this defect is kind of, it's like an atom sitting in vacuum. One of the interesting properties of this defect is that if you shine white light or green light on it, it emits in the red. And it has a very, very simple energy diagram. So you can see it has 3 levels in its ground state. This is a result of the fact that it consists of 2 holes, 2 missing electrons in the full shell of this defect. And the ground state is an ms equals 0 state, namely completely independent of magnetic field. And the 2 excited states here are ms equals plus and minus 1, and they follow as a function of magnetic field. Their energy depends on magnetic field with a very well-known G factor of the electron. So it's this physics that we know and understand and can rely on that will help us to connect the measurement that we'll be doing, which is a fluorescence measurement, and reporting magnetic field. In its ground state, it turns out that if I shine light on this defect for long enough means a microsecond or so, it will initialize this defect in the ms equals 0 ground state. Interestingly, the fluorescence of this defect, when I shine green light on it, it emits in the red, depends on whether I'm in the ground state or any one of the excited states. The fluorescence in the ground state is brighter than it is in the excited state, so this allows me, just by measuring fluorescence, allows me to determine whether my electron in this defect is in its ground state or any one of the excited states. So how would I use this to measure magnetic fields? The simplest version is to basically say, well, let's add a microwave signal to this defect. The microwave will try to induce transitions between the ground state and one of these excited states, but I don't know the frequency that would cause this excitation at any unknown magnetic field. So what I'll do is I'll ramp up the frequency and I'll look at the fluorescence. And once I hit the correct frequency that satisfies the condition where the energy of the photon equals the energy separation of the defect, I will start mixing the ground state and excited state, and my fluorescence will dim. And so I'll know that that's the magnetic field in the system. There are many other ways of using this defect to measure, to report magnetic field, but the essence is quite similar, and it gives us a rather precise way of determining magnetic fields, precisions of nanotesla or so. Another great advantage of this defect is that it is temperature independent. It is diamond, so nothing is really changing that much when I cool the system down or heat it up. So I have a magnetic field sensor that is very convenient at many different temperatures. And if I want to have spatial resolution, note that this defect is atomic in size. So if I can bring it close enough to something of interest, I would have magnetic field spatial resolution that I can report simply dictated by the distance of the defect to the system of interest. And so over the years, we've been developing these type of probes. We've turned the diamond, a bulk piece of diamond, into a scanning tip, where at the apex of this tip, we have one single defect, one single nitrogen vacancy center that we can now scan around. And in fact, this pillar here is part of the diamond matrix. The same thing here. They're not attached. There's material that's removed surrounding it. And so this is all one monolithic piece of diamond, and the photons emitted, the fluorescence that emitted from the defect, they are basically collected through the pillar that acts as a waveguide into our optical recovery system. And of course, the tip also serves as an atomic force microscope that allows us to navigate real space when we're approaching a sample. So in the spirit of today's description, what we know how to measure is fluorescence. We use the physics of this defect, which we understand well, and we can report magnetic fields. I haven't told you, but this defect, in fact, can also report electric fields and temperature, all as a function of position and frequency. It's most sensitive to magnetic field, but it has these other qualities as well, again, using slightly different physics that I haven't described here, which basically using our understanding of how this level diagram changes with temperature or electric field allows us to report these quantities while measuring still fluorescence. And again, we can basically, now that we know how to report magnetic field, we can basically claim, hey, we know how to measure magnetic fields, and we can use additional pieces of physics to report additional quantities. And before kind of diving into a specific example, let me just tell you of a variety of things that we've been doing over the course of several years. We're always measuring or reporting magnetic field, but each one of these arrows represents a different piece of physics that allows us to probe different physical properties of a system. So just to give you a few examples, you're familiar with magnetic resonance imaging systems. These are systems that measure the density of protons in our body. They have spatial resolution on the order of a millimeter. So using this defect and our ability to measure magnetic field as a function of frequency, we were able to construct a three-dimensional magnetic resonance imaging technique with nanometer spatial resolution rather than millimeter spatial resolution. And the physics here is basically fluctuation dissipation theorem. It's the relation between the fluctuating spins of the object we're interested in and the decay of the electron spin inside our sensor. We're able to image the texture of these skyrmions that I mentioned before. This might seem to you like a very simple arrow, basically just using Maxwell's equation to connect magnetization and magnetic field. It turns out that it's a very tricky arrow, and the reason is that if you tell me the magnetization, I will be able to predict what is the magnetic field. The inverse is not correct. So if I know what the magnetic field is above a sample, there are in fact an infinite set of magnetizations that produce precisely the same magnetic field. So just Maxwell's equations are insufficient to report the magnetization texture. In fact, you need additional information, and here the information on the topology of this defect is the one that completes the picture and allows you to make this connection. In superconductivity, there is something that's called superfluid density, and so we can relate magnetic field to the superfluid density. In the seminar yesterday, those of you who were there, I talked about measurement of spin chemical potential. So just like electrons, if I have long-lived spin excitations, they can be described with a chemical potential, and we can probe chemical potential of spins, again, by reporting magnetic fields. This is a study that explores hydrodynamic flow, just like you have for gases or fluids inside a pipe. Basically, very strong interaction between particles. These are electrons flowing in a sheet of graphene. And as you know, when a fluid flows in a pipe, it forms a boundary layer. Because of the shear viscous forces of the fluid, it turns out that electrons, under certain conditions, behave exactly the same. And here we're basically taking advantage of the orbital motion of the electron that generates magnetic fields. And so we can report the current density as a function of position. And this last example, I'd like to dive in just a little bit further. This is the detection of these neutral spin excitations. And then I'd like to tell you a little bit about what we could use them for. So here is a piece of magnet, and I have localized electrons. They each carry a spin, and the interaction between these spins, they're wiggling, they're pushing on one another, leads to spin waves. And you can think of these spin waves as propagating spin waves. Because a spin generates magnetic field, these spin waves are generating magnetic fields that are propagating waves. They have an amplitude and a phase, and the phase is position dependent, and it's a time-varying magnetic field set by the frequency of the spin wave. So it turns out that using our NV spin, we can probe directly these coherent spin excitations. And the reason is that my NV spin has 3 levels. If I focus only on 2, it's just a 2-level system. It's characterized by a Bloch sphere with unit radius. And it turns out that a time-varying magnetic field that is resonant with 2 of the levels will lead to rotations on this Bloch sphere. So if I initialize my spin in the ground state, the North Pole here, it turns out that this time-varying magnetic field can be thought of as an operator that wants to rotate my spin from the North Pole to the South Pole around this axis. But what's really unique here is that the position of this vector in the equator, what direction is it exactly pointing at, depends on this phase. And so if I were to look at different locations across the sample as this propagating spin wave is evolving, I would see that this axis is rotating in space. But in order to really see this, I need to do some interference experiment. I'm not going to describe it in detail, just to show you that we can actually visualize these spin waves in real space. Each one of these lines here is a wavefront of these spin waves. You can read off what the wavelength of this excitation is. It's a few microns, maybe 3 or 4 microns here. And each one of these frames is a snapshot of the propagating spin wave. So I want to emphasize, we're imaging here propagating spin waves, not standing waves. And the reason we see contrast is because we are basically changing the amplitude, the total amplitude of this magnetic field that the NV sees as the spin wave is propagating underneath our tip. So this is nice. We could visualize these neutral particles. And the question is, what can we do with them? So I'd like to digress just a tiny bit and tell you about scattering experiments. So scattering experiments are experiments that you're all familiar with. You have some object, you shine some light, coherent particles or radiation on it, and you're looking somewhere far field, and you'd like to infer from what you're seeing far away, tell you something about the object that is scattering your particles. In a more precise formulation, we have some coherent source. It has a well-defined energy and momentum. We have an object of interest that scatters these particles. These could be neutrons, these could be photons. And the key of a scattering experiment is that we are imaging things far away from where the particles interact with our material. The whole idea is that we're getting some picture on the screen where the particles are non-interacting. We know their properties really well. And then if we can extract or measure both amplitude and phase of the scattered signal, we can reconstruct what we all know is the structure factor, the thing that scattered these particles. Scattering experiments are used in many, many different applications to do optical aberration correction for imaging, galaxies. Neutron scattering is used, so coherent neutrons are being used to measure the dispersion of spin waves in momentum and energy. Electron scattering can give us information on real space down to atomic structures. And of course, X-ray scattering gives us structure. So it's a very prevalent technique. And what I'd like to ask is, well, can we use our spin waves that are coherent, and we can generate coherent spin waves that are propagating with well-defined energy and momentum? Can we do a scattering experiment with spin waves? Now, unlike the other particles that I mentioned, spin waves do not exist in vacuum. These are particles that live inside a solid only. And so we need a vacuum. And our vacuum is going to be some thin slab of a very high quality magnet. You can see it here in our experiments. This is YIG. YIG is kind of the best, or one of the very, very low loss magnetic materials. And you can generate spin waves in YIG that propagate millimeters without nearly any decay. The way we launch the spin waves is we have this metal electrode that we position on our vacuum, on our slab. We send an alternating current through it that generates an alternating magnetic field that wiggles the spins and launches spin waves with a frequency given by our modulation. And the wave vector is dictated by the dispersion of the material. So this material has some dispersion of these spin waves. We select omega, the material selects K. And the idea here is that we let these spin waves, they propagate. We then put a target, a material of interest, on top of this vacuum. And we are imaging the spin waves with our NV center, just like I showed before. And what we'd like to do is to image the scattered spin wave pattern, extract amplitude and phase, and infer something about the scatter. Yeah?
As you pointed out, there are lots of systems, such as light, wave systems that we can use to perform scattering. What is the motivation for using magnons to perform scattering?
Great. So I mentioned neutron scattering in the exam just one slide ago. Neutron scattering is actually a very, very powerful technique to measure spin structure factor, basically magnetic excitations inside a solid. But imagine that my target is a monolayer of some material, maybe a layered magnet. So the volume of material that I have is tiny, and in some cases, the density of magnetization inside this material is very, very small. Could be maybe 1 million or 1 billion times smaller than what you'd find in a regular magnet. And so these conventional techniques are not going to be able to resolve, to basically give you a sufficient signal that you can work with. This technique is really geared towards mesoscopic samples, so micron scale objects, perhaps even interfaces. Suppose you have something happening at an interface between two materials and you'd like to explore that. So it's not going to replace all the tools that we have, but it has a particular goal, which is to address mesoscopic phenomena in magnetic materials. Thanks. All right, so I've already shown you the propagation of magnons as they're moving towards our target. And I didn't explain in detail how we measure amplitude and phase, but I do want to emphasize that these are propagating waves. They're not standing waves, and we're going to be using our NV center to measure both the amplitude and the phase of the scattered waves. And for that, we need to do 2 experiments. So I'm going to show you 2 images. One is an amplitude image. So here is our target. And by the way, I didn't mention what this target is. This target is a very thin magnet, but different type of magnet than the one that makes our vacuum. And you can see that the amplitude of the spin waves surrounding the target is very complex. So obviously there's an interaction region. In fact, the interaction region is much greater than the target itself, maybe not entirely unexpected, but it basically means that this is really complicated. But you see that once I go into the far field, I'm starting to see an image that makes a little bit of sense. It's angular, just like in a scattering experiment. I can go further and further. I'm going to just see these features spread out more and more. And if I now turn on our ability to measure the phase as well, you can again see a very complicated evolution of what happens to the phase of these wavefronts. But again, in the far field, we get something that's pretty simple. And we can try to now use this scattering amplitude and phase to reconstruct what is it that scattered our signal. So I want to emphasize that, again, we're kind of going through layers of measurement apparatus. So we used an NV center to measure magnetic fields, and now we're using the magnetic field detection to be able to measure spin waves, and now we're using the spin waves yet as another measurement instrument to explore some new physics of materials that we can place on this device. And the cycle continues. This is really kind of what we're about. So I want to give you first an expectation. What is it that we expect the target would be? And I'm not going into details, just very high level. It turns out that our target is a magnet, and what scatters spin waves, it turns out, are gradients of the magnetization. I'm not explaining why, but you have to trust me. So if this is the target and it's magnetized in this direction, the gradients of the magnetization appear only on the top and on the bottom and should disappear in the middle. So this is the kind of reconstruction of the target that we expect from our measurement. And despite the fact that this is a very simple example, this is what we actually measured. So we are seeing that the entire target is scattering our spin waves in a way that we, still looks like a dipole, but in a way that we don't understand in detail. And this is a great example of the flaw of developing a new measurement technique, The problem here is that we don't understand very well the physics connecting what it is that we know how to measure and what we want to report. And the reason is that there are many, many things that can scatter spin waves, and we need to kind of understand that physics better. It could be exchange interactions, it could be dipolar interactions. The time-varying magnetic fields of the spin waves can drive currents in our sample. These also will scatter magnetic fields, spin waves. There could be elastic and inelastic scattering. So all these things need to be worked out for us to be able to really use this as a kind of solid technique, and this is work in progress.
How do you collect the spatial resolution of an image? Like you showed a couple of XY plots. Are they produced by producing the same configuration over and over and scanning with the probe different locations?
Yeah, so imagine that, so I'm launching so everything is done here at steady state. So I have a steady state flow of spin waves towards my target. And any given point here, there is an amplitude, there is an oscillating magnetic field. And I just know, and I could, if I come an hour later, it's going to be the same oscillation, and it's going to have a well-defined phase in relation to my drive. And I know how to measure this quantity, and I can integrate as long as I need to get good signal to noise.
So what's the spatial resolution?
Oh, so the spatial resolution is the distance of my probe to the sample, and that could be maybe 20 nanometers, or even less.
So the total number of spatial positions you're measuring the field at is how many?
20 nanometers.
No,
I'm measuring
to make it
each.
like you showed us right there.
Yeah, so this is maybe 20 microns by 20 microns. And each pixel is 20 nanometers by 20 nanometers.
Okay, so 1 million measurements?
Yeah. Another question.
Yeah, I want to clarify. So is it like, if you know phases of scattering, then you kind of, generally speaking, can reconstruct the scattering potential? Is
Correct.
that kind of idea?
Yeah, so of course, ideally, you just take the amplitude and phase, you inverse Fourier transform, you know the Green's function, and you get your target. That's theory. In experiment, there is noise, and there is a convolution that I need to undo, having to do with the spatial distance of my probe, for example, from the sample, etc. And all that gives me noise. So we've tried to do this kind of inverse process, and it's not working really well. What is working well is a forward approach, basically to say, well, let's assume my target is something. Let's calculate what, and I can parameterize this target with, monopoles or multipoles. And I will basically add terms until I get something that looks close to my experiment. It turns out that we can't really get very close. So we don't know how to describe the target, and partly it's because we lack understanding of the physics that really scatters the spin waves. So there's more work to be done. But yes, both the deconvolution approach and the forward approach are things that we're trying.
The lowest multiple, which is dipole.
Right. Yes, but it turns out that it's not enough. A dipole, I don't have it in this slide stack. I can show you later. But yeah, a dipole looks very, very different from what we're seeing. So there are details in this object that I was showing. It's not just a dipole. It has a quadrupole and an octupole. And even that is not enough. Yeah.
What are the frequencies at which you are driving these spin waves at?
This is of order of gigahertz.
Okay, and is there like a high, like a limitation, highest frequency that you can drive and collect data?
Yes. So NV centers are sensitive to microwaves in the gigahertz range. So we can, in principle, go to frequencies that are maybe several gigahertz. We're now pushing it towards 10 or 20 gigahertz. And one needs to kind of invent new methods if one wants to take it up to the terahertz regime. It's not impossible. We have some ideas that we haven't tried to implement, but it gets harder and harder for an NV center as you go to higher and higher frequencies. Lower frequencies are rather easy. So going to, kilohertz or hundreds of kilohertz, that's easy. Higher frequencies are hard. Jay.
So what's the advantage or comparison of this Magnon scattering to, let's say, I brought that line, I directly applied the magnetic field to your target and just measured the magnetic field response. I kind of just have the yellow line closer to your disk. I'm just probing it with the NV center. I would get some kind of magnetic response as well.
So it's very complicated, right? So, if
I didn't have the
Oh.
So if I did the experiment without the
So you'd get some magnetization, but you're not.
stability and
Yeah, so.
stability as well.
Well, it's going to be kind of a long wavelength. So here you can, in principle, change the wavelength of your particle. So you're basically measuring some S of Q and omega. So you're really getting the full structure factor, ideally.
But on a micron scale, right?
Well, that's what I'm just showing you. So right now we're pushing down to submicron to the order of 100 nanometers. And whether we can get down to tens of nanometers, that requires much higher frequencies that are harder to reach. But yes, we are trying to push to shorter and shorter wavelengths. Okay, so before moving on to the second probe, let me just again put this in the context of kind of the measurement scheme. Measure fluorescence, report magnetic fields, spin wave theory to get structure factor. And I'd like to now spend a little bit of time telling you about a different sensor, which is a sensor that can report potentials. And again, with some spatial resolution on the order of 100 nanometers or even less. So to explain what is the physics that governs how to connect, how to report potential, I'd like to start with this kind of thought experiment. I have a bucket and I'm pouring sand and I'm watching how the mass or the weight of this bucket is increasing over time, and it's going to increase with time. But if I were to look very, very carefully, because the sand is granular, what I would note is that the mass is increasing in steps. It's not continuous. And what I'd like to ask is, can I create an analogous experiment for charge? So I want to be able to pour charge into a bucket and see how the charge increases in my bucket, and to see whether I can see the discreteness, the granularity of the electron charge. And I think you'd all recognize that this kind of apparatus is something that you all are very familiar with. It's basically a capacitor. In a capacitor, I can apply a voltage, and that voltage will increase the charge, let's say, on this little plate in a way that is linear. And again, in the same spirit of granularity, if I were to zoom in very, very carefully at this curve, I would see that charge is not increasing continuously. I could only add charge in units of the electron charge, and so I would get these kind of discrete steps on this curve. Now, a different way to see how charge is added to a capacitor is from an energy perspective. And we know that if I have a capacitor and it has a fixed voltage, I could ask, well, what is the energy of this capacitor as a function of its charge? And we know that it's quadratic, goes as 1/2 CV squared. And the nice thing, of course, is that the minimum energy arises when the charge is given by CV. So that's why the capacitor wants to have this amount of charge when the voltage is V. But now remember, charge is no longer a continuous variable. It's a discrete variable. And so I have to look at this curve at specific values of the charge. I can't just choose any value. And of course, one situation would be that if I were to look really carefully at this curve, I would find that the minimum energy indeed appears for an integer number of electrons in the system. But if I tweak the voltage just a little bit, trying to increase the charge, the minimum of my parabola is no longer going to appear for n electrons. It wants to be a little bit higher, but that's not allowed. So the ground state is still going to be n electrons. And if I increase the voltage a little bit further, still the ground state is going to be n electrons until there is a magic special situation where the energy of n electrons and n plus 1 electrons exactly are equal. And at that point, if I push the voltage just a tiny bit further, I would add one more electron to the system. So I want to point out that these two conditions are very, very different. This one is a condition for which the ground state is n electrons in the system, and this one, the ground state, is equally probable for n and n plus 1 electrons, and there is a very nice way in which I can distinguish between these two situations, and that is by adding electrodes to my little plate. So if I were to add two electrodes such that I'm trying to send current, very weakly tunneling, so very weakly coupled to the plate, but I'd like to try and send current from this left electrode into my plate and back to the out one, you see that under these conditions, current is not allowed because the ground state is n electrons. In order for current to flow, the charge of this plate has to change. It needs to go from n to n plus 1 back to n. This is forbidden. But if I change the voltage just a little bit and I end up in this configuration, now current can easily flow. I can go from n to n plus 1 and back to n, and there's nothing blocks the current in this configuration. So the response of this device, the current through my little plate, is very, very dramatic. It changes from current flowing to no current flowing every time one electron is added to the system. So it's a very, very sensitive electrometer. I could count these peaks and know how many charges I've added in units of 1 electron charge. And of course, I could sit at some very steep position here and be sensitive to tiny, tiny variations of potential. Now, one thing that is important is to understand the limitations of a technique. So we didn't talk about what is the voltage difference that is associated with going from n to n plus 1 electrons. And also we didn't talk about what sets the width of these peaks in current. So it turns out that the width is given by temperature. So this means that I like to be cold. And the separation, delta V, we can calculate simply by asking, well, what is the voltage that is needed to change the charge by 1 electron? And we can plug in what we know for the capacitance, and we see that delta V is inversely proportional to the diameter of my little disk. So this means that if I were to make this sensor with a bigger and bigger diameter, eventually what's going to happen is I'm going to lose my sensitivity. So the two requirements for this potential sensor are, one, to have the disk be small enough so that I could resolve individual peaks, and that at kind of reasonable temperatures of, let's say, 1 Kelvin, 100 nanometers is enough. And the second is to be at low temperature so that this width is going to be resolvable. This phenomena, by the way, is known as Coulomb blockade. It was discovered in the early 1990s by these three gentlemen who won the Buckley Prize for this. So as before, now that we know how to report potential, we can use additional chapters of physics to connect to interesting physical phenomena. And again, just a few examples before diving into one specific example a little bit deeper. So one thing that we know how to do, and I'll talk more about this, is to report fractional charge. So we'll see that using this technique, I could really visualize the existence of fractionalized particles inside a material. I didn't talk about it, but we can resolve phase transitions that involve spin. So these are spin phase transitions that we can detect using this probe. And another example that I just like to highlight, this is a very forefront topic today. These are churn bands in various 2D systems. It turns out that this sensor can easily detect what is the underlying topology of the bands in the system. And again, what is the connection between topology and potential? I haven't described, but it's a very interesting arrow here. It's a very interesting piece of physics that allows us to connect potential to topology. But I'd like to tell you about fractional charge. So let's start again from just electrons moving in the plane, and if there's no disorder, no magnetic field, they're moving in straight lines. And if I subject them to magnetic fields, the electrons localize. They're all moving in circles. If there was some disorder, the electrons will move along constant potential orbits. And if the magnetic field is really strong, you can think of them as moving at the valleys or the peaks of this potential landscape. They become localized in space, and this is going to be extremely important. So we can image the fractional charge only when it's localized in space. If it's moving, we need a different technique. But in this system, which is a two-dimensional electron system subject to a very strong magnetic field, charge becomes very tightly localized. So why is localization important? Imagine we have our sensors sitting above our 2D system, and we can change the charge on this 2D system just like we've done when I described the technique, basically using a capacitor. So I have some gate, and I could add charge to my 2D system. But if my 2D system is very big, then the voltage that I need in order to add one charge is given by 1 over the area. If the area of my 2D system is very, very big, that voltage is going to be tiny, and I won't know that I'm adding individual electrons to the system. It's going to be just a smear. But this is very different in the case where the electrons are tightly localized, because now what's going to happen, when I change the voltage on the backgate, I need to add charge to these localized pockets, 1 electron at a time, so the system will show very abrupt response when an electron is finally able to enter one of these localized states. And so if I were to imagine a measurement where I'm scanning along, let's say, a line, and I'm asking, well, at what voltage of the backgate do these charges enter, I'm going to see something that looks like that. You might wonder, why are these curved? So as a function of position, I'm basically going to see, well, an electron enters here and here and here, and it enters when the density is at this value. The reason I'm showing it curved simply because my tip could have a little bit of charge, and so the charging condition of an electron into this pocket will depend on how far my tip is from the location of the localized site. But this is kind of the signal that we expect to see, and let me show you indeed that is what we see. So here is a kind of artistic rendering of the potential that we have in our system. We're scanning along the black line, and when we do the experiment that I just described, you see these dark features. Each one of them represents, as a function of position, adding an electron to the system. So the way to think about it is, as we're changing the density, we're hitting this black line here, 1 electron fills into this pocket, and then as we continue to raise the density, another electron falls into the next pocket, and this process continues on and on as we're filling more and more electrons into the system.
Do the electrons have to tunnel to get there?
Yes, they have to tunnel to get there.
And the time for tunneling is short enough that you can see it in your experiment, evidently?
Yes, so these experiments are very slow, and again, everything is steady state, so I could, lower the density and I'll see these electrons going out one at a time. So once they go in, they're there. And if I take them out, then they're out. The charge is very stable in the system. Okay, but now the crux is, what happens if I didn't have electrons? I had exactly the same potential landscape, but instead of electrons, I had fractionalized charge. So remember, the voltage that's needed to add a fraction of a charge is going to be a fraction of the voltage. So if I added over this course of this density change 3 electrons, I will see also a total change of charge of 3 electrons, but this will occur with 9 events because I'm now adding. It's much easier to add charge. I can add it a third at a time. So it turns out that when you go to the fractional quantum Hall regime, exactly this happens. The potential landscape remains unchanged when you go from electrons to fractionalized charge. And indeed, what you see is that the number of lines tripled, but they appear at precisely the same locations as we had the electrons before. So here we're really seeing explicitly how fractions of charge are filling up these localized charge pockets as opposed to electrons. And again, in the spirit of what do instruments measure, yeah.
How do I calibrate to make sure that, let's say, my capacity is not changed between these two cases?
So the capacitance to the tip or to the back gate?
The previous slide had the 3, right?
Yeah.
So there was bunch of coefficients as well, right?
Yes.
So how do I make sure that we did these 2 experiments?
So, right, the axis here is the voltage difference between the back gate and the 2D. It doesn't depend on my tip. My tip is an observer, so this voltage scale here, what is the voltage that's needed to add 1 charge, is directly related to the size of this pocket. For a small pocket, it's going to be a larger voltage. For a bigger pocket, it's going to be a smaller voltage. So what you're asking is, when I go from filling factor 1 to filling factor 1/3, could it be that this pocket changes?
And also the x-axis is the back gate, right?
It's a back gate.
And then I use some capacitor or etc. to relate it to the number of particles in my pack.
Yeah, this distance is not changing.
I can assume that that's
Yeah. It's, I mean, you can have some quantum capacitance, etc., but these are all kind of very, very tiny corrections to the geometric one. Yes, but the puddles are actually bigger than the distance to the gate. So it's really a parallel plate capacitor. And you can do statistics, and when we were actually looking to observe fractional charge of E/4 at filling factor 5/2, we did a lot of statistics because things were varying, etc., to get a charge of E/4. Here, it's very very visual, very easy.
I have a question.
Yeah.
Is there history since when you lower the voltage? It means like when you emptying the electrons, is it reproducible?
Yeah, very reproducible. These images are very stable. Yeah.
So to change the filling factor, say from 1 to 1/3, do you change it by gate or by changing magnetic field?
It turns out you could do either, and the potential landscape doesn't change. Yeah, and the reason is that when you're away from integer filling or from a gapped state, it could be integer or fractional, when you're away from that filling, you have carriers that screen your potential. So in fact, the potential landscape is very smooth. Your density is inhomogeneous. Once you enter a gap, the picture reverses. Your density becomes constant because your Landau level can only accommodate a fixed number of charge, and your potential becomes visible. But it doesn't matter whether it's a fractional gap or integer gap, this potential landscape that sticks its head out is always the same. And we have shown that. Right, so I'm coming to the end. So that was visualizing charge. And so my last slide here is basically, again, to the younger members of the audience. It's very fun to understand a new piece of physics, but we rarely ask ourselves, well, what can we do with it? And there could be some technological applications. What I'd like to encourage you is to think, well, what could I use that physics in order to connect a quantity I know how to measure and a quantity that I'd like to report? This is how new instruments are built and designed, and this is, I think, something that is extremely important for the development of the field. So with this, I'll just stop and acknowledge the group members who've contributed to the work. And thank you.
What do you dream of measuring?
Oh, so many things. I mean, you know, it's a trick question, I think, right? My dream is to stumble upon something that I didn't expect. And my approach to satisfying this dream is to try and probe quantities that are, you know, have not been very carefully looked at. So that's why we're kind of really crazy about developing new measurement techniques, new ways of looking at materials. Hopefully something in that will produce a surprise.
Maybe to help with that dream, you do radio frequency SET, so you can measure very small time resolution.
Yeah.
Can you do that?
Yes. So this is, you know, Rob Shulkopf has demonstrated that many years ago, the RFSET. So you can definitely push these techniques to high frequency. The real question is, what system would that be interesting to do? So for example, you could ask, well, can I do a high frequency measurement in the quantum Hall regime? And the answer is no, because it's a very high resistance system. And basically, if you ask, can I bring, I mean, there was the question, how long do I need to wait for a charge to come in? Actually, to bring a charge in the quantum Hall regime to the middle of the sample takes a really long time. The sheet resistance could be 10 to the 15 ohms. So you really need to find the right physics.
I have a
Yeah.
proposition.
Okay, good.
I have a proposition for that. So
Very good. Perfect. Looking forward to hearing it.
I have another suggestion. Ever since high temperature superconductors are supposedly not describable, their fluctuations are not describable by just a Gaussian state, like of a linear field or system. So I always wondered, why don't experimentalists measure like 4-point correlation functions of a high TC superconductor and just exhibit the non-factorization of the correlation function to try to understand the nature of the state that way. And I've asked various experimentalists, and I think the answer I got was always, well, yeah, that would be nice, but it's impossible to do. So, but you're telling me that you have this localized probe. You could use not one probe, but 4 at a time. You could look at interference between them. So could you use it to measure higher point correlation functions of interesting materials?
100% yes. Absolutely.
Have you done it?
No, it's not easy, but we have various proposals. In fact, you know, just a couple of months ago, we put out a paper exactly about that. You actually don't need to measure with 4 probes. 1 probe is enough if you can do some clever extraction of the information of the, so you extract temporal correlations rather than spatial correlations. But you can do it either by spatial correlations or temporal correlations. We were thinking more of applying this to, you know, spin liquid candidates, but I guess high TC superconductors could also be a good candidate to explore that. So I think the answer is yes. Not easy, but yes.
Some of these seem to refer to two-dimensional structures. Have you thought about doing any biological membranes, neurons or something?
We haven't. This is a domain that Ron Walsworth has done some beautiful work. He's here looking at both neural response, magnetic fields generated by neurons, and other biomatter. I understand very little about biological systems.
Yeah, but this is a tool and that's a
Yes, yeah. So the tool, and the tool I think is being, and it's being developed further. I haven't described the developments of using these kind of NV sensors for doing studies of molecules and dynamic response of neural networks. Yeah, there is work done there, not mine.
Do you have a question? Any other questions? So maybe I'll ask them one last one. So again, I guess this charge sensing and quantum Hall, and you've been doing this for a little while. And at some point there was this vision that somehow you could get towards a topological quantum computer or something, or any upgrading or stuff like that from just, not quite grading necessarily, but establishing the amnion character of fractional chose and so on. So what's...
So it depends on what system. So, if you're talking about, right, so at 5/2, I think the answer is potentially yes, because the anyons carry charge. In other systems where you might have fractionalized charge, they might not carry, and non-abelian character, they might not carry charge. But yes, I think there are some interesting ideas of how to extract, to perform fusion and to read out the fusion outcome of two non-abelian particles, and they will have an electrostatic signature that you can pick up with this technique. So the answer, I think, is interesting. Yeah, yes.
Yeah, so, but what do you, in your view, is the time scale or difficulty?
I think it's the quality of materials. We try to do things of that nature in gallium arsenide, but I think those are much more disordered than graphene. So I think it might be that in graphene systems, which you could really find regions that are microns and microns with 0 defects, that you can maybe do something like that. But it requires further tool development, right? Because you need to bring two of these anyons and controllably bring them together and separate them, etc. So do this kind of real space fusion. How you do that while monitoring something happening all on a scale of maybe 50 nanometers is hard.
Okay, so that was